In this video, we're going to explore the integrals, exponential, and logarithmic functions. We're going to write the definition of a natural log as an integral. We're going to recognize the derivative of the natural log. We did that in one of our previous videos, but we're just going to review some of it again, and some of it may be new. We're going to define the number e through an integral. We're going to recognize the derivative and integral of an exponential function. Again, I know we did that in a previous video. We're just going to do some more. We're going to prove properties of logs and exponential functions using integrals. We're going to express general logarithmic and exponential functions in terms of natural logs and exponentials. So assume that we have not ever defined a natural log or the number e or an exponential. I know we've done it in pre-calculus 1, we defined it in pre-calculus 1, but let's just assume we've never done that before. So for x greater than 0, let's define the natural log of x as integration from 1 to x of 1 over t dt. Now let's take a look at the curve for just the right side of the curve, just the right side of t being 0. So we're just going to look at the right side of the graph, which t is greater than 0. So for x greater than 1, we would be doing the integration from 1 to some x value. So 1 to x of 1 over t. Now, we know that we can change the limits of integration by multiplying by the negative 1, and then, so instead of going from 1 to x, we're going from x to 1 of the negative integral of 1 over t dt. And what that allows us to do then is to look at the area under the curve from some x value, where the x value would be greater than 0, all the way up to 1. Now notice when the natural log of x, is equal to 1, the answer is 0. And that's because if I go from 1 to 1, 1 over the integration of t, well, we know when the limits of integration are the same, so from 1 to 1, of course, its integration would be 0. So if we define the natural log as integration from 1 to x of 1 over t dt, then if I go from 1 to 1, then it has to be 0. And the function y is equal to 1 over t is greater than 0 for all x greater than 0, because it's the area above the x-axis. And all of the outputs from 1 over t is always going to be above the x-axis when x is greater than 0 and when t is greater than or equal to 0. It can't be equal to 0. And it's clear that the natural log is increasing when x is greater than 0. So as we go out this way, if this is how we define the natural log of being 1 over x, 1 to x of 1 over t dt, and you can see if x is somewhere out here, that will happen is that the area will continue to increase, which means the natural log itself must be increasing. So then we know that if we take the derivative d dx of the natural log of x, in other words, we're taking the derivative of the integration, we end up with 1 over x, and that comes from the fundamental theorem of calculus. We also get that the function L of x is differentiable, therefore it must be continuous. The domain that we are looking at, f of x equals natural log of x, is 0, non-inclusive, so this is a typo. Let me go ahead and fix this. This goes from 0 to infinity, not negative infinity, because you can't take the natural log of a negative number, and the way that we defined the natural log means that if we define the natural log of x as being the integration from 1 to x of 1 over t dt, where x is greater than 0, t is greater than 0, then obviously that we have to have a domain where it is larger than 0. So 0 to infinity, non-inclusive. Here's some properties that we discovered, and we discovered these in pre-calculus 1, so we're just going to go over them again. The proofs are in your book. We didn't really prove them rigorously in pre-calculus 1. We just said this is it. So we know the natural log of 1 is 0. The natural log of the product AB is the natural log of A plus the natural log of B. The natural log of a over b is the natural log of a minus the natural log of b, and the natural log of a to the r is r, the natural log of a. Now, again, these shouldn't be new to you, but the proofs, the formal proofs for these are in your book, and they are new. We never proved them before. We just said, hey, this is true, so accept it. If we then say, hey, let's take the natural log of the absolute value of x, then we actually get to extend our domain, provided, of course, that x still cannot equal 0, but allows us to include x being a negative number. Then the derivative with respect to x of the natural log of the absolute value of x is still 1 over x. And this gives us some integration formulas that should be familiar to us. Right here, the integration from 1 over u du is the natural log of the absolute value of u. And this is why we have to put the absolute value on that value that we integrate. So if this is 1 over, say, x plus 1, then this is the natural log of the absolute value of x plus 1. And this is why we have to have it. Before in Calculus 1, we just said, hey, that's nice, let's make sure we always do that. Well, now this is why. The reason up above is why. We then say, let's define e. We're going to define e as the natural log of e is equal to 1. And another way that we can think of this is that the area under the curve, where y is equal to 1 over t between 1 to e, from 1 to e, is 1, and e must be equal to 2.71282846 each, give or take, each. And so we now define e in terms of the natural log and in terms of integration. Something we haven't done before. Now, note the natural log is a one-to-one function, therefore it always has an inverse. And we're going to denote this by the exp, or x at e to the x. E to the x. So e raised to the natural log of x is equal to x. That's what this is saying for all x. And the natural log of e to the x is equal to x. That's what this is saying for all x. And you're going to see on the homework that sometimes you have to write exp. Sometimes you can write e raised to the x. Just depends on who coded it. And of course, we know that when we have functions that are inverses, they are reflected over the line y equals x. So this point, which is in the natural log of x, is 1, 0. Its inverse becomes 0, 1. Here's another definition. We say, for any real number x, define y is equal to e to the x, to be the number which the natural log of y is equal to the natural log of e to the x, which is equal to x. And of course, we get these properties of exponential functions, and all of the proofs are in your book for your viewing pleasure. Now you're like, why is this different than what we've had before? Well, it's not. We're just now defining it more rigorously in math. Before, we didn't really define it as rigorously, and that's because our math knowledge at that point wasn't where it is right now. So now let's go to the general logarithmic and general exponential functions, where we have f of x is equal to a to the x. Sometimes you may see an exponential function defined as f of x is equal to a b to the x, where b is the base. In this book, we're going to use a instead of the b. We're going to have base a. For any base a greater than 0, for any number x, we're going to define y is equal to base a to the x as y is equal to a to the x, which is the same thing as saying e raised to the x, the natural log of a. Now, if we define that for an exponential, y is equal to a to the x, then we take the derivative of this, the derivative with respect to x of a to the x. This becomes d to the x, e to the x, e raised to the x natural log of a, which we know based on our derivatives of e to the u, it's going to be x natural log of a multiplied by the derivative of the exponent, which is the natural log of a, which is then just a to the x natural log of a. Now, we said in Calculus 1 this was the rule. Now we're starting to actually define it and prove it. So if we have general exponents now, here is the theorem. Again, any of these proofs are in your book for your viewing pleasure, and we will go over them in class if that's what you would like to do. So we have d dx, the derivative of this a to the x with respect to x is a to the x natural log of x, and it was always just a given. Now we're actually proving it. And if we integrate a to the x dx, and this is where we're really kind of like, aren't we doing integrations? Yes, we are doing integrations. And if I have a to the x dx, and we know it integrates to 1 over the natural log of a to the x plus c. Then, of course, for the generic log base a, d dx, the derivative of the log base a of x with respect to x is equal to 1 over x natural log of a. Again, the proofs are in your book for your viewing pleasure. So now they're asking us to find the derivatives, and you're like, well, wait a minute, I've done this before. Yes, you have, absolutely have. And all we're asking you to do is just refresh some derivatives, and then, of course, that helps us to integrate. It's like when we do divisions, we like to refresh multiplications. When we do subtractions, we like to refresh additions. So I'm going to rewrite this as 1 over x, the natural log of x. That way I can use the product rule. So when I use the product rule, d dx of y is going to be equal to, I'm going to actually rewrite this again as x raised to the negative 1, the natural log of x. So when I have x raised to the negative 1, its derivative is negative x raised to the negative 2, natural log of x. And then plus, now I'm going to do the derivative of the natural log of x, which is 1 over x, multiplied by x raised to the negative 1. Now I'm just going to clean this up a little bit and write this as the negative natural log of x over x squared. Now, because they're both, this is also going to become x squared, I can write it all over x squared, and so I can write it as 1. And that's my final answer. Now on b, d dx of y, this is going to be the chain rule, so it's going to be 1 over the sine of x multiplied by the derivative of the sine of x, which is the cosine of x, which is the cosine of x over the sine of x, and I can rewrite this if I want to as the cotangent of x. On C, what I'm going to do is I'm going to bring that 7 out front using the laws of logs. So I'm going to bring this 7 out front first. So I have this is going to give me y is equal to 7, the natural log of 4x. Now when I take this derivative, d dx of y, this will give me 7 multiplied by 1 over 4x multiplied by 4, which just gives me 7 over x. Now with d here, I'm going to have to use the chain rule twice. So d dx of y. So it's first going to be 1 over the cosine squared of x. Now I have to take the derivative of cosine squared. This is going to give me 2 cosine of x. That is the derivative of the squared part. So I'm going to have to do the chain rule one more time. Now I'm ready to do the derivative of the sine, or derivative of cosine, which is negative sine of x. Now this becomes negative 2 sine of x over, this cosine will cancel with one of those, and so it'll be negative 2 the sine x over the cosine of x. I can leave it like that, or I can write it as negative 2 the tangent of x. For this next example, I can do one of two things. Now this is square roots, so I can multiply the square roots together. So I can say this is y is equal to the square root of x squared plus 1 multiplied by x squared minus 1. So this is going to rely heavily on some algebra. And so this is going to be the square root of x raised to the 4th minus 1. And I can write this as y is equal to x squared minus x to the 4th minus 1 raised to the 1/2, and I can use the chain rule. Totally fine to do that. If you're like, man, I don't want to use a chain rule, then we can do it with logarithmic differentiation. So I can take the natural log of both sides. I have the natural log of y is going to give me the natural log of the square root of x squared plus 1 multiplied by the square root of x squared minus 1. So the natural log of y is equal to, well, because of the fact that this is a multiplication, this is a product, and it's x squared plus 1 raised to the 1/2 and x squared minus 1 raised to the 1/2, I can use two of the log rules that says this becomes 1/2 the natural log of x squared plus 1 plus 1/2 the natural log of x squared minus 1. Now, when I take the derivative of this, I'm going to get y and dy dx, because I'll write it dy dx multiplied by 1 over y. And then on the other side of the equal sign, I would get 1/2 multiplied by 1 over x squared plus 1 multiplied by 2x, because that's a derivative of x squared plus 1. And then plus 1/2, and then multiplied by 1 over x squared minus 1 multiplied by the derivative of x squared minus 1, which is 2x. So I get dy dx multiplied by 1 over y is equal to, and I'm just going to clean this up just a little bit, and so I get x over x squared plus 1, and then plus these 2's will cancel, giving me x over x squared minus 1. Now I can't leave this as dy dx times 1 over y, so I'm going to multiply both sides by y. So I'm going to multiply both sides by y, and when I do that, I'll have dy dx by itself. Dy dx is equal to, now remember, y was the square root of x squared plus 1 multiplied by the square root of x squared minus 1. And then inside of the parentheses, we're going to have x squared plus 1 plus x over x squared minus 1. Now, believe it or not, this is going to be the same answer as this. I think this one is one that I probably would not have done with a logarithmic differentiation because I think it's easier to do it algebraically and then take the derivative of this, and it's actually a nice cleaner answer algebraically than this, but this is totally fine to have done it that way. You could have approached this two different ways. Now, let's take a look at the next one over here. This one with f and g, there's no way of getting around f and g without doing the natural log of both sides. Well, actually, what am I saying? F, you absolutely can do it without taking the natural log, but g, you absolutely need to. So dx of y is equal to e, the sine of x, multiplied by the derivative of the sine x, which is the cosine of x. And that's as good as that one gets. Now, for g here, I'm going to write this as the natural log of y is equal to the natural log of x raised to the negative 1 over natural log of x. Natural log of y is equal to, now this is an exponent, so it'll come down out front as a multiplier, so it becomes negative 1 over the natural log of x, multiplied by the natural log of x, which was already there. So you can see this ends up becoming negative 1, which is really kind of nice. So then the natural log of y, the derivative of the natural log of y, the derivative d dx x of the natural log of y is going to be 0. So this is equal to 0. Now when I multiply both sides, because what I end up with is dy dx multiplied by 1 over y is equal to 0, I'm going to get dy dx is just simply equal to 0. With h, I can do logarithmic differentiation, but I think it might just be easier to add the exponents. So this is y is equal to x raised to the 1/2 multiplied by x raised to the 1/3 multiplied by x raised to the 1/6, which is x raised to the 1/2 plus 1/3 plus 1/6. Now the common denominator is 6. So then this is y is equal to, let me see, the first one will be 3 over 6. The second one will be 2 over 6. And the third one is just 1 over 6. And that's because I multiplied the first fraction by 3 over 3, the second fraction by 2 over 2, and this, of course, is just the same. Oh, don't forget my x. There's my x raised to the. So I end up with y is equal to x raised to the 6 over 6. So y is equal to x dy dx is equal to 1. And I think that's going to be much easier than trying to take the natural log of both sides, but it's up to you. Now we're ready to do the integration. Now, the first one you can totally integrate without doing any u sub if you realized that the derivative of this is just 1 dx. And so this becomes the natural log of the absolute value of 3 plus x evaluated from 0 to 1. Now you always should put the absolute values on, but since 0 and 1 are going to produce a positive number, in this case you could go without the absolute values. So this will be the natural log of 4 minus the natural log of 3, and I'm perfectly satisfied if you leave the answer just like that. For this next one, it's a little bit more interesting. I can't just take the natural log right out of the gate. So what I'm going to have to do is refresh myself about long division. So in other words, I have x squared plus 1 is going to divide into x to the third plus 0x squared plus 0x plus 0. Long division of polynomials. X squared will go into x to the third x times, and so I'm going to get x to the third plus x. Now I'm going to subtract this polynomial off, and I end up with just negative x as the remainder. So this becomes the integration from 0 to 2 of x plus negative x over x squared plus 1 dx. Now the first part of this integration is pretty straightforward. It's just going to be x squared divided by 2. Now this, if you realize that the derivative dx of x squared plus 1 should be a 2x, and you realize that a 2 is missing, then this will become a negative 1 over 2, the natural log of the absolute value of x squared plus 1, evaluated from 0 to 2. Now, if you're like, what? How did she do that? Well, let's just do a quick little u sub here and say let u equal x squared plus 1, and du would equal 2x dx. That means 1 over 2 du would equal to x dx. And that's how come I knew that this is going to be the natural log of the absolute value of x squared plus 1. And this negative needs to come out front, and I needed the 1/2. So that's where I got to that. Now I can do the evaluation, and so this is going to be 2 squared over 2 minus 1/2, the natural log of 2 squared plus 1, and then minus the 0 squared divided by 2 minus 1/2, the natural log of 0 plus 1. And you can see this goes to 0, and the natural log of 1 goes to 0. So my final answer is 2 minus 1/2, the natural log of 5. And I'm totally fine if you leave it in that form. For me, in fact, I would prefer that rather than a decimal equivalent. All right, so let's take a look at my next example. Now, if you remember up above, I took cosine of x over the sine of x, and I said I could write that as the cotangent. But if you remember, to get cosine over sine, that must have meant that I started out with the natural log, absolute value of the sine of x plus c, because u sub, we let u equal the sine of x, and du is equal to the cosine of x dx, and you can see that I have the nice easy u sub, and I don't necessarily even have to do u sub on this one. On D, I'm probably going to do u sub just because I may get lost in all of it. So I'm going to say, hey, let's let u equal the natural log of x. Then du would equal to 1 over x dx. Now, if I rewrite this from 2 to e of 1 over the natural log of x, the quantity squared, multiplied by 1 over x dx, you can see that right here is my du, and this is u squared. So then this integration becomes 1 over u squared du. And as I've said multiple times, I'm going to replace my limits of integration rather than using dummy variables, because I'd prefer just to replace my limits of integration. When x is equal to 2, u is going to equal the natural log of 2. When x is equal to e, u is going to equal the natural log of e, which is 1. So this is going to go from the natural log of 2 to 1. So this is the integration from the natural log of 2 to 1 of u raised to the negative 2 du. Now I'm going to add 1 and then divide by that negative 1. Remember, what I just wrote is not part of the original problem. That's just there for my housekeeping purposes. So I end up with negative u raised to the negative 1, evaluated from the natural log of 2 to 1, which gives me negative 1 over 1 minus a negative 1 over the natural log of 2. So I end up with negative 1 plus 1 over the natural log of 2, and that is my final answer. I'm going to leave it just like that. I think that's it. Yep, that's it for this video. Nice short video. Some of the stuff we've done before, so it's not really anything surprising. In fact, I think we did it last week. Anyways, that's it for this video, and we'll see you in class.